Continuing on with section 6, now that we have an understanding of how ions are behaving and why they do what they do, we can now write the electron configurations for them. When you're writing electron configurations for elements in the D block, remember that electrons are always removed from the outermost energy level first. So that's not going to be the D block. So keep that in mind. So let's write the electron configurations for the following ions. This is what I recommend doing. First, write the configuration for the neutral atom, then deal with the charge. So forget the chromium 2 plus part, just let's write the configuration for chromium. If you remember, chromium is actually an exception. It's going to reference argon, and then it's going to be 4s1, 3d5. So that's the electron configuration for just chromium. Now we have to take into consideration the positive 2. When something is positive, that means it's lost electrons, and in this example, it's lost 2. Where do we pull those 2 electrons from? Don't pull them from the 3d yet. They always pull from the outermost energy level first, which would be the 4s1. So we need to remove 2 electrons, one of them being from the 4s. So that just goes away. We don't need to write 4s0. We still need to remove one more electron. Well, the only other place to remove it now is from the 3d5, because now that is the outermost energy level. So now it becomes 3d4. You might be asking, wait, it's d4, so don't we have to do that trick? Well, we can't, because there's no electrons in the outermost energy level anymore. So the final answer, we could clean it up, would be argon and then 3d4. What about titanium 3 plus? Well, let's just write out titanium. Titanium is going to reference argon, and then it's going to be 4s2, 3d2. So that's regular titanium. Now we need to take into consideration that it's 3 plus, so we need to remove 3 electrons. Remove from the outermost energy level first. So these 2 electrons in the 4s are gone. We need to remove one more electron. This 3d2 now becomes 3d1. So I'm going to rewrite that without the gap, just like that. Finally, iron. Normal iron is 4s2, 3d6. Because it's iron 3 plus, I need to remove 3 electrons. So I'm going to remove these 2 first, and then I have to remove one more electron. Therefore, iron 3 plus will have the configuration of 3d5. Let's let you do some. I want you to pause the video and then hit play to reveal the answers. Alright, so let's take a look and see how we did. So we have the silver ion, which, remember, silver is an exception as far as its normal configuration. And so make sure that you had it originally as 5d or 5s1, 4d10, and then the one electron that gets removed is this one right here, resulting in this is the answer. And then for sulfur, sulfur was a different one because sulfur actually is an example of an anion. So instead of removing 2 electrons, you need to make sure that you added 2 electrons in order to get the ion configuration. So that would be 3s2, 3p6, which, if you noticed, this is actually the configuration of a noble gas argon. So it could have been written as either or. Making the notation that it is argon is probably the better one because you notice now sulfur has that noble gas configuration. Alright, so now let's talk about orbital diagrams because orbital diagrams build right on electron configurations. When we look at electron configurations, all they tell us, going back as an example, all they tell us are the first 2 quantum numbers in that we know what energy level that we're in, if you take a look at the examples here that I'm highlighting, and we also know what shape the electrons are in, and so we know the second quantum number. But then that's it. We don't get into specific orbitals, and we don't get into the spin. So orbital diagrams actually provide that information for us. They build on it. So orbital diagrams are pictorial representations of electron configurations. So we've been spending a little bit of time talking about how to figure out the electron configurations. The orbital diagrams are just simply what we add on. And you'll notice that we have boxes that represent orbitals. So all these boxes that you see are going to represent those atomic orbitals we've been talking about up until now. And remember, every orbital, regardless what orbital we're talking about, can only hold 2 electrons maximum. And when you have two electrons in those orbitals, they have opposite spins because of that fourth quantum number that we talked about. Now, some quick vocabulary or terminology here. There's two terms we need to be aware of. There are elements that are known as being paramagnetic. And paramagnetic are elements where there's one unpaired electron. Doesn't matter where it's at, it just has to be an unpaired electron. So, as an example, and let me clean this up a little bit, lithium would be an example of a paramagnetic element because it does have one unpaired electron. So would boron. And as you can see, most elements are paramagnetic. And what does that mean, paramagnetic, other than just we know, okay, it has an unpaired electron? It means that it is going to be affected by a magnetic field. Whereas elements that are diamagnetic do not have any unpaired electrons. All electrons are paired up. And so we can see examples of that would be like beryllium and neon. And so they aren't going to be affected by a magnetic field. All right, so when we're thinking about filling up atomic orbitals, remember the Aufbau Principle. We stated it already a little bit before, but I want to come back to it. Electrons always have to fill from the lowest energy level to the highest. So if we take a look at, an element that has these available orbitals here, they're not going to start filling up here because these are higher energy orbitals. Instead, electrons are going to fill from the lowest energy level, and then once that's filled, then the next, and then once that's filled, they'll start filling out these. Now, it's important to know that these orbitals right here are all going to have the same energy. So this orbital, and this orbital, they all have the exact same energy. It's just different orientations on the XYZ axis. So when it comes to filling electrons in these orbitals, it's good to remember that all these orbitals here in the circle are the same energy. So really, actually, it doesn't matter which orbital gets filled first with regards to filling these three. So let's take a look at another example, and we're going to start looking at how you do an orbital diagram for that. So to get started, before we even do the orbital diagram, let's write out the electron configuration for selenium. All right, so locate selenium, which is element 34, and using shorthand, we're going to reference argon. And then from that, argon, we're going to fill out 4s2, 3d10, and then 4p4. 4p4. All right, now we're going to get our orbitals ready to go. Now, we can draw orbitals like boxes, or to make our lives a little easier, we can also draw orbitals just simply as lines. And so that's what we're going to do. So we're looking at an s subshell here. How many orbitals does an s subshell have? Remember, it just has the one. That's why it can only hold maximum 2 electrons. When we're in the d subshell, that has 5 orbitals, 2, 3, 4, and 5. Because remember, that we need 5 orbitals to hold 10 electrons. And then for the p subshell has 3 orbitals. Because a p subshell can hold 6 electrons maximum. In this case, we don't have 6, but nevertheless, we still have the 3 orbitals. All right, so we're going to go ahead and start now filling in our electrons into these orbitals. Now, when we go to fill in these electrons, remember it has to fill in order of increasing atomic orbital. So it would fill the 4s first, then it would fill in the 3d, and then it would fill in the 4p. That's the Aufbau principle that we just learned. But what about filling up the orbitals within the subshell? Is there a rule there? And there actually is, and that rule is known as Hund's rule. So Hund's rule states that when we're filling orbitals with electrons, if there are multiple orbitals that exist within the same energy level and shape. So for example, we have multiple orbitals here in the 3d, and we have multiple orbitals here in the 4p. So when that happens, the rule is 1 electron needs to go into each orbital until they have paired up. This often is known as the fighting siblings rule. And here's why. Let's suppose we had a family of 4, right? So you have the parents, right? The 2 parents, and then you had, 2 kids. I'll just indicate them by being smaller. Okay, and you moved into a 4-bedroom house, right? So each square is a bedroom. Well, it's probably assumed that, okay, the parents are going to take one of the rooms, but then your kids are probably going to be thinking, okay, this kid will go into one room, and then the other kid would go into this room, right? That's probably how they would be thinking. Well, what if you as the parent say, okay, no, actually, you both are going to share a room. I don't think that your kids would probably like that very much because they're thinking, why would we have to share a room when there's 2 other rooms available? That they would fight, right? That's the idea there. And so the idea is each electron, just like each kid, would want their own room if it's available. I have heard it another way, and this is actually interesting to me. Gentlemen out there, you may be able to relate to this. It's also called the quote-unquote urinal rule. When you go into a bathroom, you don't double up if you don't have to, right? You space yourselves out, and it's only when you absolutely have to, that's when you'll double up. And to be honest, sometimes not even that. Sometimes you just use the stall. It's safer. But the same idea, right? These are different analogies to show that if there is an orbital that's empty, they need to be filled with electrons before doubling up. Also, another way Hund's rule needs to be considered is all singly occupied electrons, or I should say all electrons in singly occupied orbitals, they have to have the same spin. So for example, if you look down here, you have a single electron in each orbital. But why is this one spinning down and the other 2 are spinning up? That would be a violation of Hund's rule. So keep that in mind. So if we go back and we have to fill in our electrons, let's keep that in mind. These 2 electrons, one just has one spin, one has the other. That's not too difficult. But now when we have these multiple orbitals here, when I fill these 10 electrons, I need to fill 1, 2, 3, 4, and 5. And now that every orbital is filled, now I can double up. 6, 7, 8, 9, and 10. Now you may be thinking, what difference does it make because they're all going to be filled anyway? You're right. In that example, because there were a full 10 electrons, how you draw it doesn't make a difference. But when you come over here to these 4 electrons, if I fill them like this, 2, 3, and 4, that's violating Hund's rule because there's an empty orbital, yet I've doubled up electrons. Instead, what I should be doing is I should put 1 electron in each orbital, and now that 4th electron I can double up. Now, and here's the kicker. Remember, all 3 of these orbitals here are technically all the same energy, right? We talked about that previously on this slide right here. It's just drawn differently. So where do I put that 4th electron? I could technically put it right here, and that's totally fine. It's probably driving some of you nuts that I did that, but that's to prove a point that it doesn't matter. All 3 of these orbitals here are in the same energy level and same shape, so they're all the same energy. So that 4th electron can go in any of these 3 orbitals here. All right. Lastly, we get to the Pauli exclusion principle, and we've talked about this before. The Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. They can be in the same energy level, they can have the same shaped orbital, they can even be in the same orbital, but they cannot have the same spin. They have to have opposites. So when I see things like this, that is a violation of Pauli exclusion principle because that's saying those 2 electrons have all the same 4 quantum numbers, which is not possible. So we end topic 3 by doing some practice with example 17. We want to take a look at the drawings below which represent orbital diagrams and state which rule or rules are being violated. So let's take a look at a few together. In this first one, I see that there's some doubling up and they have the same spin. That's a violation of Pauli exclusion principle. In this second one, we have singly occupied electrons. They should have the same spin according to Hund's rule. In this last one, it looks like there's a violation because you're looking at why is it doubled up here versus doubled up here. But remember, all 3 of these orbitals shown here all have the same energy, so it doesn't matter where we double up. So actually, there is no violation in this last one. In letter D, there's a violation because we've doubled up while there's an empty orbital. That's a violation of Hund's rule. In letter E, we see that we have 4 singly occupied orbitals. They should have the same spins, but they don't. That's another violation of Hund's rule. In letter F, this doubling up right here, they have the same spin. That's violating Pauli exclusion principle. And finally, in this last one, notice that we're increasing energy. Well, somehow we've skipped this orbital and this energy level to start filling up a higher energy level. This energy level and shape should have been filled up first. This actually is violating Aufbau Principle. That wraps up topic 3.